Today we are going to discuss another variation of the induced electromotive force, which is what we call the motional electromotive force. Motional electromotive force is is the electromotive force that is usually generated when you have a conductor moving in a uniform electric field. Okay, so this is where the word motional comes from, because it is generated due to the motion of a conductor in a magnetic field. Sorry, not electric field, in a uniform magnetic field. So let's consider a specific example and try to derive an expression for this motion electromotive force for this specific example. Our specific example is where we have a bar, a conducting bar, and it is insulated. In other words, it is not in contact with anything else. And we assume that somehow we are moving this to the right by an external with constant speed. Okay, so we pushed it somehow, and then we maintained it moving with this constant speed here. Okay, now once this happens, then in this case the electrons, a conductor has free electrons, which are the charge carriers, and they are within the material of the conductor. They are flowing in every direction. Now all these charge carriers, which are the electrons here, are moving now to the right with a velocity v, constant velocity v, in a uniform magnetic field that is directed towards the page. And therefore, when you have a charged particle moving in a magnetic field, then as usual we have a magnetic force acting on these electrons, and it is given as usual by QV cross B. Okay, and when you do this, and because these are electrons, then these electrons will feel a magnetic force directed downwards, because it should be perpendicular to the electrons and the magnetic field. So these will feel force directed downwards. So the electrons start to get drifted as this moves on with this constant speed. They start to get drifted downwards, now leaving upwards a positive charge. Now as this goes on, this is of course the force that is acting on them in this case, because the angle between V and B is pi over 2. So QVB sine pi over 2 is just QVB. Now, as this happens, then you have positive charge building up and negative charge builds down. And the meaning of this is that we will have now an electric field that starts to build up. And it's directed from up to down, as you can see here. This is the direction of the electric field, the orange one. Okay? Now, once this starts electric field directed here, the other electrons, other than the electrons that have that remained here, these electrons will start to feel, in this case, a force which is QE. But since these are negatively charged particles, then this force will be against the electric field. So the electric force will be directed upwards. So as this continues to move, then we will have this accumulation of negative charge here and positive charge here will continue, and this again will lead to an electric field which will increase as the charge builds up here. Now this can increase until it reaches a point where the magnetic field, the magnetic force on the electrons downwards is balanced by this electric force upwards, and this is what we call the steady state. And in this case, the net force on the electrons will be equal to 0, so QE will be equal to QV, or we come with this expression. Okay, so E will equal to VB. Now, under this condition, the potential difference, there is a potential difference across the bar. And this potential difference is just E, the electric field, multiplied by the length of the bar. But since this electric field now in the steady state, when it is balanced by the magnetic field or the magnetic force, is equal to VB, then this delta V is equal BLV. You substitute for E VB and it gives you this expression. So you can see that this delta V, in this case, the potential difference that builds across the two ends of the bar depends on the magnetic field and the speed with which this bar is moving, as well, of course, as its length. So, and this tells you that the reason why this potential difference built up is actually the magnetic field present. Okay? So this is a general situation. Whenever you wave any conductor in a magnetic field, then there will be a potential difference generated across that conductor, okay, due to the presence of the magnetic field. So this is what we call the motional potential difference that generates across any conductor. Now, this is irrespective whether this conductor is a part of a circuit or not, okay? It is just a general thing. Now, things get interesting, more interesting, if this bar, for example, was a part of a circuit, okay? So, for example, we assume that this bar has zero resistance and this is sliding on a ray, and then there is another wire here which has a resistance. So this is a complete circuit in this case. Now, in this case, as this moves and this potential difference is generated across it, this will act as a battery or as an electromotive force that will induce a current that it will be circulating, in this case, in the circuit. Okay? So now, in this case, we have a motional electromotive force, Okay? And one way of, we can, of course, most easily find this motional electromotive force by applying the Faraday's law. Why is this so? Because now we have this circuit now is a loop, and there is a magnetic field here in the loop, and as this moves, the area of the loop is changing, and so the magnetic flux is changing, and so we can apply Faraday's law to find this electromotive force that is generated in the loop, and we will see that it is nothing but the BLV that is the potential difference that was generated across this bar, even in the absence of the remainder of the circuit. Okay? So let's see how we can find this motional electromotive force. Well, first of all, let's see what is the flux through this circuit now, this loop. Now, this is moving with a velocity, constant speed v, or constant velocity v to the right. Now, at a given instant, assume that this is so that this distance is x. Okay? Then at that instant, of course, this x is increasing, because if this is moving to the right, this x increases. But a given instant, assume that this distance is x in this case. The magnetic field in this case, let's take it to be uniform, and so the flux in this case, because the magnetic field is normal to the plane, it is just, and in uniform, it is just BLX, which is the area, Lx is the area multiplied by B. This is the flux. Now, the motion electromotive force, or the electromotive force according to Faraday's law, is given by minus d phi by dt, minus the rate of change of the flux. Now, B and L are both constants, so the only thing that varies with time is x. So dx by dt, we take the derivative of x with respect to t. But what's dx by dt? It is v, the speed with which this is moving, because it is the rate at which this x, the position, is changing. So it's just the speed of this end, which is nothing but the speed or of the bar. So the motion electromotive force that is generated is just minus BLV, and of course we know why this minus sign is. We have discussed this when we talked about Lenz's law. So this is exactly the motion electromotive force, or the potential difference that was generated across the bar, even in the absence of this the remainder of the circuit. So this is the motional, the electromotive force that will be generated in this case. If you want to find the current, you just divide this electromotive force by the resistance, and you get, and will be the current that will be flowing here, assuming that this and the bar and the rays here have negligible resistance, almost zero. Now we come to a very important point, which is the energy transfer that takes place when a motional electromotive force is generated. Now we have just seen that when you have this moving, then there is a current flowing in the circuit, and the current flowing in the circuit means with time, then there will be power dissipated in the resistor here. Okay, so there is energy transferred from, there is first electrical energy, and this electrical energy is transferred into internal energy, which is heat that is dissipated into this resistor. Now in a normal circuit, we have seen that, and we have checked actually, that there you have a source of electromotive force, and the power provided by that electromotive force was equal in the steady state to the power dissipated in the resistance as required by the conservation of energy. Now here we don't have a battery. We don't have a battery, we don't have electromotive force, and therefore where does the electric force, which is generated, which is then transferred into power or internal energy or heat, if you like, that is dissipated in the resistor, where does it come from? What is the energy transfer that is taking place in this case? Let's investigate that and try to understand this. This energy transformation situation or process here is actually one of the most important energy transformations that is of relevant to our civilization. I will comment on it just once we talk about it. Okay, so let's find first what is an expression for the energy dissipated in the battery. What's the energy dissipated in the battery? It's I square R, the general expression. When there is a current passing through the battery, then I square R is the energy dissipated in the battery. But IR is the potential, so it's IV. IV means IE, because I have only a single resistor here, so it's IE. And what is E? The electromotive force. What's the absolute value of the electromotive force? It is BLV. So the power, electric power that is transferred to the battery, to the resistor, and dissipated as heat dissipated in the resistor is IBLV. Okay. Now, okay. So we must have similar power provided by something else, so that to satisfy the conservation of energy. Now, what we have, the situation here is we have to keep in mind the following situation. Now, when this starts moving, okay, and there is a current generated, keep this in mind now. This is something that you have to understand. Now, apart from the force that we talked about, that would act on the electrons and pull the electrons down and polarizes this, there is, once the current starts to flow in the circuit, and particularly in this, then actually you have a situation where you have a current. For example, in this case, it's flowing upwards. The current is flowing upwards as per Lenz's rule. You can check that. And this current is, this conductor which carries a current is moving in a uniform magnetic field. And therefore, it will feel a force IL cross B. IL cross B. Okay? Because it is just a current carrying conductor or wire, straight wire in a uniform magnetic field. And the direction of this magnetic force on the bar, which is due to the current that it's carrying, will be to the left, as you can check by the right hand rule. Okay, just try to check it. It's very easy. I L cross B. Okay, B is into the page, I is upwards, so L cross B, it is just to the right. Okay, so as this, because of the motion of this bar, magnetic force will be generated to the left. Therefore, to keep this moving with a constant speed or a constant velocity, you must always apply a force equal and opposite to this magnetic force. What does this mean is that when you try to move this in the presence of a magnetic field, you feel a resistance. Okay, it's not just like trying to move it in the absence of the magnetic field. When you try to move this in the absence of a magnetic field, and if you assume that you have friction here, any force will accelerate it. But in the presence of magnetic field, no, because there is a magnetic force acting to the left. So you have to have an applied force to the right, equal and opposite to the magnetic field, to the magnetic force, so that you have this moving with the constant speed that you need. Okay? So in the presence of a magnetic field, actually here, moving this bar is like moving a bar in water, for example. You will feel a resistance, okay, due to the presence of the magnetic field. And this resistance is nothing but the magnetic force that acted to the left. So we know now that we have to apply, have an applied force here to maintain the constant velocity of this bar as it moves to the right, so that it continues generating this current form. So we have an applied force equal and opposite to the magnetic field, so the magnitudes are the same. Now, this force now, when it is working, when it is acting on this bar and it is moving it, okay, it's doing work on this bar. This force is doing work on this bar, okay, this external applied force. And the power provided by this is just, by applied force, is the applied force multiplied by the speed. This is the instantaneous power. Now the speed is constant, but the applied force when the speed is constant is equal to the magnetic force. And what's the magnetic force? IBL. Because it's I L cross B, the angle between L and B is pi over 2, and so it is just ILB or IBL. Okay, this is L. So IBL multiplied by V. So this is the power, the energy per unit time provided by the external force to the bar. Now this is exactly equal to this as an absolute value. Okay, so this is exactly equal to the electric field. So we can see now electrical conservation of energy. So the energy that is dissipated by the resistor here comes from the energy that is, this is the conclusion, the energy provided by this applied force is transferred via the magnetic field environment into electrical energy and then into internal energy dissipated in the resistor. So the energy that is dissipated in this resistor is actually has its origin in the work done by the external applied force to move this bar. So this is the energy transfer that is taking place. Okay. Of course, here the resistor is just the load resistor. So you want to use electrical energy to change it to heat up a resistor. For example, it might be a light bulb, it might be a kettle, it might be a stove, electric stove, whatever is that. But this might be a motor, it might be any other circuit element that utilizes electrical energy and change it into other forms of energy. So the energy that needs to work any device here is actually provided by the motion of this, by the work done by the applied force on this bar and making it move. This is the, and to have this happen, you must have this setup. You must have this happening in the presence of a magnetic field. So what's happening here is that the magnetic field here plays actually the environment or the setup through which mechanical energy, okay, which is the work, mechanical work done by the applied force on this bar, is transferred into electrical energy and then into any other form of energy as required by the circuit element that you want to utilize that electrical energy in. That might be, if this were a resistance, it will be heat energy or internal energy. If it's a motor, it will be another mechanical energy. If it is whatever is that, whatever you like. Okay, so that's the energy transfer that is taking place, and the presence of the magnetic field here is crucial for this energy transfer to happen. Okay, so the energy is not transferred from the magnetic field; it's transferred actually. It's coming. Its origin is the mechanical energy, the mechanical work that is done by the applied force to move this bar. Now, this energy transformation is the backbone of our civilization. This is how electrical power is generated. You know, of course, we don't have time to discuss generators in details, but the principle is the same. apart, as I mentioned before, apart from photovoltaic cells, usually electricity is generated using this principle. So let me give you an example. You know that, for example, one way of generating electricity is to have large turbines, for example, put under waterfalls, and as water falls, it rotates a turbine, and this turbine it's rotating in a magnetic field. Okay, so what's happening in this case is that the mechanical energy of the water is transferred by work to rotate that turbine, and this mechanical energy is transferred into electrical energy, which then comes to our house and we utilize it, and we transfer it to our cookers, to our lights, to our TV, computers, you charge your mobile phones and so on. But the original process in which we generate the electrical energy that is needed for this is actually the transfer of the mechanical energy, in this case of the waterfall, okay, into electrical energy, but in the presence of magnetic field. It is exactly a bit more complicated setup, but the principle is this, the principle of this. Okay. This is a checkpoint that it is good to do in details.